else?
Throwing my pencil.
Cambridge goes, who got you? Who got you this? I said, stop asking questions. She goes, oh, okay. Yeah, but my mom's birthday is the 6th, so I just get her one big gift.
That's really nice.
I'll get my mom a gift.
All right.
Just give her
So-
one gift.
The last chapter, we're talking about having two different samples at a time. So it's still hypothesis testing, but we're comparing different sets of data. Today we're going to specifically talk about dependent samples or matched pairs data. It's been a while, but we've talked about matched pairs before. What does that mean? Matched pairs. They match.
Yeah, something like that.
They're related in some way. So it might be like a pre-test and a post-test. I'm taking your score from two different assessments, so I'm comparing you to yourself. It might be that I give you a partner to study with for a test, and then I'm going to compare you and your partner on something. So in some way, those values are linked together, okay? In order to be able to do any hypothesis testing, we have all of our criteria, which is kind of, most of it we're not going to verify, I just kind of assumed. It has to be obtained using simple random sampling. You know, if you have bad sampling to begin with, you're not going to have good data. Has to be matched pairs. If we're doing matched pairs testing, the data has to be matched pairs. Normally distributed with no outliers, or the sample bigger than 30. So that's the big thing. Either it has to be normal already, or I have to have more than 30. And my samples have to be independent. What does it mean to be independent? They're not related. So just because one happens doesn't change the probability of the next one. Okay, so then hypothesis testing. We've seen from our others. We have classical and we have p-value approaches we can take. So we're going to kind of talk through both. The null and alternative hypothesis changes a little bit with this. If we are comparing two sets of data, then the null hypothesis is going to be the same every time, and it's going to be that the mean of the difference equals 0. In other words, our null hypothesis is that the data sets are not different from one another. So in order to do it, we are going to find the difference. So I'm going to take your pre-test, your post-test, and subtract them. That's the difference. And if there's no difference between them, when I subtract, I should get 0. So the null is always going to be the mean is equal to 0. And then we have left-tailed, right-tailed, two-tailed with our not equal, greater than or less than. We know alpha is probability of type 1 error, so we have to have an alpha level every time as we go through here. Then our classical approach would be, if we're talking about the mean, do we need a z or a t? T. So we have to find our t, which is similar to what we were doing before, except it's all based on the difference. So before we do anything, we're going to take those two sets, find our differences. Then to get our t, we take the mean of the difference divided by the standard deviation of the difference over the square root of n. Then we compare that to the t for our alpha level. So remember, if you're in the shaded region, you reject. If you're not in the shaded region, you would fail to reject. The p-value approach is you find your t, you get the probability, and when do you reject? Every time, no matter what we're testing, you only reject if p is less than alpha. Alright, so this is extremely similar to the hypothesis testing with the mean that we were already doing, except the initial setup. Instead of looking at two separate data sets, we have to get a difference. So if I'm looking at this one, the following data represent the cost of a one-night stay in Hampton Inn Hotels and La Quinta Inn Hotels for a random sample of 10 cities. Test the claim that Hampton Inn Hotels are priced differently then La Quinta hotels at the alpha equals 0.05 level of significance. So the first thing you have to do is enter your data into your L1 and L2. Okay, so let's talk about this a little bit before we go any further. We're testing if Hampton is priced differently. Why would this be matched pairs data? We're comparing two different hotels. How are those related? How is it a pair of data? They're in the same city. So I took one city, each hotel in that city. Okay, to test this, we need our null and alternative hypothesis. The null, we're looking at the mean of the difference on these. Okay, we can do them as two separate sets of data, and we'll talk about that in the next section, but this one is just easier since they're related. We can look at the difference. The null should be that there is no difference, so that equals 0. Alternative, what are we testing? If it is different, which is not equal to 0. With these. We are talking about the difference. So how do I get my difference? Subtract them. So you can go through every single data point, subtract them, and enter it into your L3. There is also a faster way. If you guys use the up arrow and go up onto L3, it says L3 equals, and you can give it a formula. So if you do second number 1, that's list 1, minus second L2, and hit enter, and it will automatically subtract them all for you. So we went up onto our L3, and it says L3 equals, and we do L1 minus L2, enter, and it will give you all of those. Is that okay? If I asked you some information, could you find like the mean and standard deviation of that list? Yeah, where would we go to find it all? Stat, calculate, one variable statistics, but which list would I need to look at? L3. Okay, so that's just kind of a refresher. So does it look like there's a difference between them? What's the mean of that list? 51.4. If there's truly no difference, what would we expect? 0. Is it possible to have a negative on that mean? Can we have negative values in our list 3? Yes. How would you get a negative? If the second was more expensive than the first. So based off this, it kind of looks like the Hampton is more expensive, but let's see. So if we go into our tests, anytime we're talking about the mean, which test are we doing? The t-test, number 2. All right. Are we basing it off data or stats? Data. We could get all the stats, but it's easier. We've already entered our data. The mean of the null hypothesis should be 0. What list do I want my calculator to look at? 3, because we're testing the difference, which was our L3. So if you just do second 3, that will pull it up. Frequency, just make sure that's always set at 1. We are testing not equal, and calculate. All right, what information do I usually want you guys to write down from this? So my T was 5.271 or is fine if you just do a couple decimal places. Our P, careful, what's this mean? So we have 0.305128. All right. So if I'm using the p-value approach, when do we reject? Yeah, we always reject if p is less than alpha. Alpha in this problem was 0.05. So since p is less than alpha, we reject the null hypothesis. What that means is there is sufficient evidence to conclude. What was my alternative? What am I trying to conclude? The hotels are priced differently. We are pretty much going to do all of these on our calculator, so the p-value approach is the easiest because it gives us the probability. But you could certainly do this from the classical approach. If you were doing the classical, we would have to use our table. How many degrees of freedom do we have here? 9, because it's always n minus 1. The T alpha, we'd have to be a little bit careful because our alpha is 0.05, but I'm doing a two-tailed test, so we'd have to divide that in 2. So remember, when you do two-tailed, that's a plus or minus on this.
Thank you.
So, if I were looking at my table, my T distribution, we have 9 degrees of freedom, so we can go to our 9. My alpha is 0.025, so I would get plus and minus 2 point, I just lost it, what was it? 262. So what that means, those are your threshold values. Anything beyond those, you would reject. What is the T for our data? We got it on our calculator. The 5.27. Would 5.27 be in the shaded region? Yes. And so we reject the null hypothesis. Do you guys understand how we got both classical or p-value? Like I said, if we're using our calculator anyway, then the classical is probably less user-friendly because the probability is already there in front of us. If we had to calculate the T by hand, we would have to use the information with the one variable statistics because it's based off, you would have to have the mean and the standard deviation of that set in order to be able to do it. So you could use that formula I gave you for the For the t, it said the mean of the difference, so that's the x bar here, the standard deviation. Okay, I can look at them. Is that okay? The other option we have for testing the hypothesis, just like with the others, we can do confidence intervals. So with those, we always build a confidence interval around the mean. So we're used to doing like our x bar, our sample mean, as our center. So in this case, you do the same thing, but the sample mean, we're talking about the difference between the two. Because it's matched pairs data, we're trying to take two sets of data and combine them into one. So same idea as what we've done before with those confidence intervals. And I think, pretty sure this is all listed on your formula sheet as well. Yeah, it's got a bullet for confidence intervals for matched pairs data, like the bottom of chapter 11 there. So we could do this. The critical value, remember the T alpha over 2, it's divided by 2 because we have 2 n's. And we always have to do n minus 1 degrees of freedom. So let's talk about this one. Construct a 90% confidence interval for the mean difference in the price of the Hampton Inn versus the La Quinta Inn hotel rooms. All right, so if I were going to do this by hand, my confidence interval is mean of the difference plus or minus T alpha over 2 times standard deviation over the square root of it. All right, so if I were going to do this by hand, I need some of that information, and it's on my calculator with the one variable statistics for the difference. So the mean of my difference, that L3, is 51.4. The standard deviation of my difference was the 30.8336. In how many rooms, or how many cities did we compare? 10. And the T alpha over 2. Let's talk about finding that. If I am doing a 90% confidence interval, so what that means is I need 90% of the data to fall in the middle. That leaves 10% divided over 2 n's, so each end gets 0.05. How many degrees of freedom do we have? So you go to your table, the T distribution. We are looking at 9 degrees of freedom. And the 0.05 gives us a T of 1.833. Okay, technically because it's two-sided, that's plus or minus, but the plus or minus is already built into our formula, so we don't really have to worry about that. So the mean of my difference, 51.4, plus or minus 1.833 times the 30.836 over the square root of 10. So you have to enter the plus and the minus. Remember, when we write the interval, we do the smaller one first. So what this means, we are 90% confident the mean price difference is between 33.526, and 69.274. If we were using this to test our hypothesis, what was the null hypothesis? That the difference was 0. Is 0 included in this interval? No. So this would again tell us we would have to reject that null hypothesis because it's not in the interval. We can also do confidence intervals from the calculator. Do you guys remember where we go to? So we go into stats, tests. We want an interval. If we're talking about the mean, it's always the t value. So which one do we use? Number 8, the t interval. This is where we do have to be a little bit careful. We're basing off data, but I could very easily give you stats to go with. The list, what list did we put all of our information, the difference in? L3. The confidence interval, I said 0.9. And calculate. Right, so stat test 8. We get here, is that the same confidence interval we got by hand? So it works both ways. I want to get one out of the book, I think. Okay. I want you guys to look at page 544. We're going to look at number 9. Oh, yeah, shoot. Well, I didn't want to type this one. That's why I just made myself a note to use the book. Okay, hold on. All right, so the little background behind this, we're trying to see if SUVs are safer than cars. So this is data from an example. So we have an SUV and a car in an accident and the dollar amount of damage for each of them. Now, first of all, what we were doing only works if what's true about our data. It has to be, they have to be independent. And why would this be independent? Were all of these found in one? Like, did we just have one big pile up and took all these cars? No, it's from all these separate accidents. So I'm assuming that would be independent. If you could read the blurb, it tells you that this data was normally distributed, so we can use it. It also requires, if we're going to talk about the difference, the data has to be matched pairs. Why is this matched pairs? I mean, those are important points, but more specifically, like, how can I treat these two numbers as a pair? How are they related?
The SUV and the car.
Yeah, why are those two numbers related? We're looking at the damage, and the key is they were in an accident with one another. So I didn't take an example where an SUV was in an accident on this side of town and a car was in an accident on this side of town and compare them. They crashed into one another. And so it was one accident, two vehicles damaged in that same accident and comparing. Otherwise, if they were just from separate accidents, we wouldn't be able to look at the difference. It wouldn't mean anything there. All right, so we have to enter our data. You guys are ahead of me because you were doing it while I was going through that. So we go into stat, edit, make sure clear, don't delete, please. All right, and it is important, these are points, so you have to make sure you put them in order. Okay, and then what do I need to do at this point? We need the difference. So you could go through and subtract every single one, but the shortcut I showed you is if you go up onto L3, it says L3 equals. And if you do second number 1, it's L1 minus second L2. So L1 minus L2. It is important to do them in that order, because if you switch it and make it L2 minus L1, it's going to change how we do our alternative hypothesis. Okay, so you can get the right answer, but your hypotheses would have to change. You'd have to be a little bit careful there. So we're going to try to be consistent and always do the same thing. Now, we have to have, if we're going to test something, we need a null and an alternative. The null is assuming there is no difference between. So the mean of the difference is 0. The alternative, we want to see the question is, if an SUV and car are in a collision, does the SUV sustain less damage? So if this is my L1, this is my L2, this is where we really have to think. If this one has less damage, when you subtract, what kind of number should you get? Negative. So I need, my alternative should be less than 0. Does everybody understand that part? So now everything is entered. We might as well have our calculator do the work for us. So we can go to stat, tests. Anytime we're talking about a mean, we do the t-test, number 2. We're basing ours off data. Just so you see, if you go to stats, if you were doing stats, you would have to have the mean of a null is 0. You would have to have the sample, mean, and standard deviation for the difference. So that's what you would need if you went that route. Make sure the mean of the null is 0. The list should be L3, and we are testing less than. So our t is -2.69 if we round. The p is 0.0181. Let's say on this problem it had said that alpha was 0.05. So do we reject or fail to reject? Reject. If p is less than alpha, we reject. This means we reject the null hypothesis. There is enough evidence to conclude SUVs sustain